professor from the um, uh, uh, sorry, Nano Handling Research Center from Germany, University of Oldenburg, professor of University of Oldenburg, and I know that he is a founder of micro and nano robotics in Germany, and one of the founders in the world. And it's an honor for us to give a opportunity to share his knowledge in the area of industrial robotics and nanoscale. So he will introduce, make a short introduction and give us main application areas. So let me welcome Sergej Fatikow. So Sergej, you have 40 minutes for your presentation, and we'll have a couple time for questions later on. Thank you for coming to us.
Great. Thank you very much, Alexander, for this kind introduction, and really appreciate this invitation to join this conference and for the opportunity to present what we are doing in our lab. The topic of my presentation is industrial robotics at nanoscale, introduction and applications. Well, actually, we started this research area about 30 years ago, at the beginning of 90s. A bunch of crazy people met every year at MIT in Boston, and we discussed how to operate materials at nanoscale. And the first question we were asked, it was always the same. What exactly is the application of industrial robots at nanoscale? And we learned to reply to this question by another one. What exactly is the application of industrial robots at regular scales? And you know, it makes a click in people's mind somehow, because everybody understands immediately that industrial robotics is not about application, it's about technology, automation technology, which we provide for quite different applications. When you take a look at regular scales, of course, you will think in the first line about reliability, high throughput, low cost, and especially tasks which humans prefer not to do, or, and this is very important because we have a special environment nanoscale, people are unable to operate at nanoscale. And we are very close here in our understanding with the famous speech by Feynman about 60 years ago already. What I want to talk about is the problem of manipulating and controlling things on a small scale. Well, still, this is a huge problem here, right? And in the sense, nanohandling is intrinsic part of the nanotechnology. May I offer you a statement, a very simple statement, to create systems at nanoscale. And this is actually the ultimate goal of the nanotechnology, if you think about this. It's not only about coatings, what many people believe. Yeah? It's about building systems at nanoscale. And to create systems at nanoscale is to apply instrumentation methods enabling reliable handling materials at nanoscale. So in this sense, nanohandling is a delivering technology for nanoscale industry. And robotic nanohandling, because there are different options, but robotic nanohandling is often the only option. What is the meaning of robotic nanohandling? How we define this in the community? It includes assembly, manipulation, characterization, structuring, fabrication, measurement, and generally all kinds of operation at nanoscale where robotic technology is involved or has to be applied. And I want to stress here, has to be applied. Why? Because there is no other option. So from this point of view, nanohandling is a crucial technology to back up the nanoscale industry. And I guess there is a huge catch-up potential in Russia. So I hope the things will get better soon in this area. Impact is obvious. Yeah. Quite different products here, including NEMS, MEMS, material sensors, actuators, and actually every segment of our life can benefit from nanohandling and nanotechnology, right? Electronics, healthcare, etc. How we contribute or have contributed by my division beyond research work. So our spin-off Smaragd is a market leader, worldwide market leader in nano-positioning systems, with the staff close to 300 now. They are doing very well. We established an international conference, the flagship event in our community. I founded this 5 years ago already. The time is running off. We co-chair the IEEE Technological Cluster on Micro Nano Robotics and Automation for many years already. And last but not least, we run joint nanorobotics lab at South China University of Technology. And there is a boost actually in China now in microrobotics. They have, I guess, close to 40, 50 labs now. And as I mentioned, I hope Russia can catch up on this development. Let me show you just a few from our huge robot selection so that you get a feeling how they look like. So they're pretty small, few cubic centimeter in size. Well, like specimen positioning table, for example. So we buy, so mostly from two companies, which are world leaders on the market, spin-off from our division and PI in Germany. So these guys, for example, from PI, so this specimen table is from Smaragd. There are different resolutions, different numbers of degrees of freedom. It depends on application all the time. Stuff like this. I guess you get a feeling now, how they look like. The resolutions are quite standard, a few nanometers, what you need for many applications at nanoscale. So this guy was developed in my lab, a pretty famous one, a mobile with 4 degrees of freedom and 3 nanometer resolution. How we operate these nano handling robots? Well, we have plenty of applications on air and plenty of applications in vacuum. So why it is often necessary to put the robots into the vacuum chamber of a scanning electron microscope? There are 2 reasons generally for this technology. So first of all, of course, imaging limitation of an optical microscope. So you know the limit is at the level of half of visible wave, and this is about 200-250 nanometer theoretically, I have to say, because practically it's about, well, close to 1 micro, because you always have some fabrication deviations in optical lenses. You can never get to the theoretical limit of the optical feedback. So this is the first reason, obviously. And the second one is you have a full, or you can have a full manufacturing process chain inside the same device, inside the same vacuum chamber of a scanning electron microscope. So from the very beginning, you fabricate your nanostructures using milling etching by FIB or electron beam, for example, then electron beam induced deposition, nanobonding, manipulation by robots, measurement, characterization, quality check, etc. So you have the whole chain in the same vacuum chamber, and you can do rapid prototyping in a very easy way. So this is a very special merit of this technology. So you don't have to change devices, and you can implement your application in real time. Just one example from my lab. We have 3 of scanning electron microscopes in my lab, and FIB, and this device is pretty unique because we combined in the same vacuum chamber all what is necessary for fabrication, manipulation, and characterization. So you can see here this device. There's a closer picture of this. So you can use for fabrication focus ion beam, atomic force microscope, electron beam induced deposition, electron beam induced etching. Then for handling manipulation, obviously nano handling robots, which we operate inside the vacuum chamber, and the atomic force microscope, using this device as a nanorobotic technology, and real-time sensing using imaging from ECM, imaging from atomic force microscopy, even from FIB. So many people don't know this, but you can use focus ion beam for imaging as well. And I forgot here to mention camera feedback, obviously, for coarse positioning. Well, now when we talk about automation, how to use the scanning electron microscope as a sensor, feedback sensor in the closed loop control. So you can see how the general picture of what we are doing for automation. We can pick up images from ECM for fine positioning at nanometer scale. The resolution in the standard ECM device is about a few nanometers. So in our device is 2 to 3 nanometers. So you can use images from cameras, optical cameras for coarse positioning. They're quite different tasks, right? And then you process these images, and in your low-level controller, you calculate the adjustment of the current position of your robots and tools. Yeah. So there are special units here because we operate our robots by piezo drives using the slipstick principle. So for this reason, we need voltages of about 300 peak to peak. So we need amplifier here in this place. Everything else is just standard stuff. So this is the hard piece of automation, the closed loop. How fast you can position your robot. Yeah. So this is really the bottleneck here, obviously, because the faster you are in this closed loop, the higher is the throughput of your operation. And what is the actual bottleneck here in this closed loop? Of course, the scanning electron microscope. Why? Well, this technology is excellent technology for visualization at nanoscale with a big list of merits, but unfortunately, it is slow. It is slow. You need time to scan the region of interest. Here, for example, you can see the image from my lab. The acquisition time is 40 seconds. 40 seconds, you can forget any high throughput automation here. And what you see here is the tip of the atomic force microscope, the tool which most of the nanorobotic labs use every day. So what is going to happen if you reduce the acquisition time now? So you are going to see something like this. So the reduction in acquisition time is pretty dramatic now. We have the acquisition time of 90 milliseconds, but you can hardly recognize something, right? So it's very difficult now. And you know, in our research work in the last 20 years, we received a lot of different research awards, and most of them were given us exactly for this topic, how to increase the speed of imaging at nanoscale. So this is really the bottleneck here for automation at nanoscale. So let me finish this short introduction, just scratching on the surface a little bit here by this animation. So coarse positioning, as I mentioned, we use optical cameras here. We just implement a simple tracking here, nothing special about this. The problem is solved for many years already. Fine positioning, quite different story. This is still ongoing research topic here. We implemented a special technology using 2-line scans instead of scanning the whole region of interest. And by doing this, we can increase the performance of imaging dramatically. Update rate 1 kilohertz, so we can update the position of the robot 1,000 times a second with the accuracy of about 10 nanometers. Okay, let me take a glimpse at some ongoing projects at AMI. Well, we have many. I don't have time for all of them, obviously. I squeezed the most interesting stuff for you here. Well, additionally, most of the projects are industry-driven. So this is how we like doing this. So this is the philosophy in my division, more or less. It's fascinating to work with companies here on the on real applications. But the backside of the medal is, of course, that we have restrictions in publishing and presenting, and we are limited by NDAs, by pending patents, stuff like this. Sometimes it's really stressful. You know. We just finished work, for example, for a big player, so the company that is under the 7 richest companies worldwide. And the first step, actually, when we started our collaboration was the NDA that was as thick as some PhD thesis. I'm not joking. This is really stressful, but fascinating again. Part of our activities is service and nano handling. Of course, we make some good money by this activity, but it's not the most important point here. The most important, we can help, because nano handling is the bottleneck in companies and research labs. Only few labs worldwide can implement stuff which everybody needs now, when you develop nanotechnologies in the real way, towards real applications, toward NEMS. Two examples here, placing of a wire between two electrodes. So at a regular scale, it would be half a minute job, right? But if your wire is just 100 nanometer, so I would say you don't have plenty of options here. You need help by experts, and that's exactly what we are doing for other people. And the other example, so this spring, a company from south of Germany spent, well, I guess 3-4 weeks in my labs here using our facilities and technologies to develop COVID-19 test. Pretty successful, Yeah. Well, to some of our research projects, robotic fabrication of nanophotonic structures. Here we work together with some nanophotonic companies in Germany and University of Heidelberg. There is a high need for 3D nanophotonic structures with application of so-called designer defects. And so this is what we have implemented so far in this project using master-slave robotic handling. So we have the master here, a tool with adhesive pocket fabricated by focus ion beam etching to pick up nanoparticle. So the smallest nanoparticle we handled so far is a silica nanoparticle of 400 nano. And the slave robot is the robot carrying a tungsten needle to help the master to pick up the particle and to place the particle on the spot. So here you can see different implementations. So we can use different sizes of nanoparticles and designer defects. So we learned actually during this collaboration that having designer defects and being able to change these designer defects in the 3D structure is extremely important for nanophotonic industry. So the newest development here and in this collaboration is the technology which we developed for the first time is the combination of ion beam, electron beam, and nano bonding for multi-layer nanophotonic structures. So we apply EBIT deposition, electron beam induced deposition here, just to make one layer of nanoparticles more stable. Then we apply focus ion beam etching to prepare the surface of the first level for positioning of the second level, and so on and so on. Here you can see this in reality. So the first layer of nanoparticles, robotic handled obviously, then bonding, then FIB fabrication, milling of the surface, here the second robotic application, and so on and so on. But the most important, what we implemented recently, as I mentioned, designer defects by using of different particles, right? Because, for example, if you use particles made of silica and made of PMMA, then afterwards, after your assembly, you can selectively etch, for example, PMMA particles, and you can get assembly on demand of any possible 3D cubical photonic structure. So this is really an interesting result. The second piece of activities, what I want to present you, robotic handling of 2D materials. So in early work here, the first time we implemented the mechanical characterization of graphene membrane. So this membrane is less than 2 nanometer thick. And it was really interesting result in those times. It was 6 years ago now. The technology is simple actually, yeah? So everybody knows this characterization and calculation of Young's modulus if you can follow the deflection of the membrane and measure the force of this indentation, but try to do this at nanoscale. And here you can see the merit of integration of all this technology inside the same vacuum chamber, because you can use ECM imaging in real time to pick up the deflection of the membrane here, and you can pick up the force from the piezoresistive EFM cantilever. So you have everything then to calculate the Young's modulus of this membrane. But obviously, we are not interested in characterization of just one membrane. We are into automation. We are robotic people. So for this reason, we implemented automated characterization of nanomembrane array inside the ECM. So the task is very simple. You have a chip with lots of processed nanomembranes made of graphene. And then you put this chip inside the vacuum chamber and you switch on the ECM and you go home, right? So next morning, all thousands of these micromembranes are being characterized. So this is the task. From the robotic point of view, nothing special. Only the special environment, right? Vacuum and nanoscale. So this is difficult to implement. Everything else is just simple to understand. So obviously, you have imaging here from the top of the scanning electron microscope. So you have to track a special pattern. So this cross pattern here on the back side of the EFM cantilever, and downside of this cantilever, you have the tip, obviously. And this tip is exactly the tool for nano indentation here. So you have to take this tip here to every single of these nanomembranes and do indentation and record the results. So this is how we prepare the automation, tip calibration, obviously. So this FIB mill cross pattern, and this is the position of the tip on the other side of the cantilever, right? So for imaging, we use template matching, for tracking, we use template matching here for tracking the cross pattern on the cantilever, and blob algorithm for detection the position of the nanomembrane here. So this is the real-time video. Let me skip the calibration just to save time, so that you see the actual operation. So the robot takes the cantilever to the first membrane. So the position of the first membrane has been detected before. So now we are doing nano indentation. You can see here the typical shadowing inside the ECM. So it's done now. Now the robot moves the cantilever to the second nanomembrane, and so on and so on. So this procedure is fully automated. This is exactly what we expect from nanorobotic handling, in terms of high throughput fabrication, just for you to get some feeling. So staying with graphene, so we developed a new technology to process graphene flakes on the top of a processed chip, which is pretty difficult, because you can do this only sequentially using, for example, the tip of the EFM cantilever. There is no other way, because you have the chip, you have the graphene flake here, and you have to process this flake to induce a new feature, for example, this graphene flake. So we use hydrogenation, oxidation of graphene here, using well-known technology of local anodic lithography. It depends on the polarity of your voltage, which you apply here between the tip and the graphene flake. You can deposit the material here on the top of the graphene flake, or you can reduce, how we say this, reduce the graphene, remove the material. And here you can see some of the results here, reduction of graphene here in a controlled way. We did this on air using light microscope. So this is one of our applications without scanning electron microscope. So again, master slave robot system here. Conductive finger is carried by slave robot just to make some flakes of graphene conductive here on the top of your chip, and piezoresistive cantilever is carried by the master robot here. So this guy is doing the real structuring of graphene here. So results are pretty solid here. The next piece, robotic manipulation of liquid metal droplets. So this is the big science, actually. Liquid metal droplets, highest potential for nanotechnology. So many labs work on this stuff, but the major problem is how to fabricate a liquid metal droplet in a controlled way. And you have a desired size of this droplet. There is no good technology, and we have developed one now. The patent here, so I can't reveal too much here from this activity. We So the other merit, yeah. So I have to mention first how we started this work. So a few years ago, we discovered a really great publication in Nature about mechanical fracturing of liquid metal. Well, mechanical fracturing is not a very good approach, of course, because you cannot do this in controlled way. You cannot achieve the desired size of your droplets. Yeah? But most important in this publication that the guys use Gallium-STAN. And this is eutectic and conductive liquid metal, meaning that you can use this liquid metal in the liquid mode inside a scanning electron microscope. So just imagine you have the opportunity to use the conductive liquid metal droplet inside the scanning electron microscope having high vacuum. Yeah? And this is really something special for semiconductor industry especially, right? So, and we immediately picked up on this idea and developed our own technology for fabrication of micro droplets using electron migration. Yeah? This is a sophisticated theory behind of electron migration. Pretty bad news for semiconductor industry. You know this maybe because your conductive ions just run away from your structure, and the higher is the density on your chip, the bigger is the problem with electron migration. So people have to handle this, but we can use this. We can use this because just take a look at this simplification. Yeah? So the amount of ions which you can produce from a liquid metal depends on the current density and diffusivity of your ions, right? And modulation of current density is a straightforward option which we have used in our development here. Just take a look. If you negatively bias your tip, then ions from the liquid metal reservoir, they run to your tip. And you can control the amount of ions running to the tip by controlling of your current. Yeah? So this is pretty linear dependency, right? It's a fantastic story here. Yeah? We didn't expect this in the first line, but it works absolutely predictable, and in this patent now, of course, we put all the details here, all the simulation, and well, again, I can't reveal too much here at the moment. You know? So the next step is, of course, to handle this micro droplet, right? So you pick up the droplet, then you transfer the droplet, and the droplet can be smaller than 1 micro. Yeah, no problem at all, because you can control the size of this droplet by current. And then you have to place the droplet on the spot. And you just make it vice versa. Yeah? It is simple then. Yeah? If you understand the procedure, you change the polarity and your tip is now positively biased. And the ions, they run away from your tip, right? So back to the surface here, yeah? And then you use the van der Waals force between the surface and a liquid metal droplet, and you can remove your tip. Yeah? It is pretty simple then. Yeah? So it works just fine. And so we run different applications now in different projects. So the most recent project, we just got funding a couple of weeks ago from German Research Foundation here for investigation of adhesion properties of surfaces at nanoscale. So there are different options how to do this. And here you can see what is going to happen if you apply a liquid droplet at different textures of the surface, right? So the more spikes you have in your surface, yeah, the smaller is the van der Waals force. So the adhesion force is getting smaller and smaller if you have a lot of texture in your surface. And vice versa, of course. On the smooth surface, you have a lot of contact area, and consequently, the van der Waals force is pretty high, and the adhesion is pretty high. So you can do force mapping here at nanoscale, and this is extremely important, especially for bio-nano applications. Well, another application which start running now is nanoprinting. So obviously, if you can induce nano droplets here in a comfortable way, you can write structures here by just pick and place of liquid material inside the ECM. Yeah? But we are just at the beginning now at this activity. So the second piece, the next piece, adhesion force mapping by laterally sensitive colloidal EFM probes. Well, again, there's a complicated theory behind of this. Just to give you a feeling here, this picture, I guess this is revealing. Yeah? If you do adhesion mapping or force mapping of texture surfaces at nanoscale, so obviously, if you use the standard EFM pull-off technology, you don't regard lateral forces in the textural surfaces. And the following happens then. Look, your probe, no problem at all here at this spot on the chip, because your probe is in direct contact here and there is no lateral influence. But quite different story here. You measure this force using pull-off technology, but the real adhesion force is this one, right? So it's a big difference. It's a big difference. And to solve this problem, it is necessary to develop special tools which have lateral sensitivity. For example, by tilting the EFM cantilever. Yeah? But it's not easy because the fabrication is very challenging to achieve this tilting. Yeah? Because normally you have just 1 degree of freedom in the EFM cantilever. Otherwise, the atomic force microscopy doesn't work. Yeah? As simple as this. Yeah? And we used robotic handling here to manufacture here, introduce new technology for manufacturing of this kind of probes at nanoscale. So combining here focus ion beam for tapering. So we just use a standard EFM tip here and remove the material by focus ion beam here. And well, I don't have a good picture here, here for maybe. So we fabricate a so-called adhesion pocket then for the probe, and then we do robotic assembly of this probe. And here in this particular project, it's just close to 1 micro, to be able to work at nanosurface. Yeah, and we use a tungsten needle here and robotic assembly here to put the probe here on the top of the column. And then afterwards, we use nanobonding here by electron beam induced deposition here. It's like gluing at nanoscale. So the only option how you can implement bonding at nanoscale. Yeah? And this is a validation of the approach. So look, this is a real small cavity which you have here, and you have absolutely no problem with your EFM imaging here. So your probe works just fine here. Yeah? And this is the implementation of the whole approach for adhesion mapping. So now you can monitor lateral forces as well. So this is the red line here. So you can compare here. In this case, for example, you don't have lateral influence at the position x0, and obviously lateral influence is 0 as well here. So you record only your pull-off force here, adhesion force at this point. But as soon as you are on the side wall of the cavity, you can monitor at the same time the lateral force, and you can calculate the real acting force at this point of the texture structure. High frequency microwave contact probing. So this is another interesting piece of work. So this is about scanning microwave microscopy, high frequency measurement here, and the influence of misalignment. So you can see here the simulation of misalignment of ground source ground probe here. If you have a little bit here rotation, parasitic rotation, you immediately have here deviation from the expected signal here. Yeah? This is the one problem. And the other problem is abrasion of pattern probe. Yeah? look at this. So this picture is from real application here. Yeah. So this is the picture of your surface of your pad here after the application of the high frequency probing. So obviously you will have unpredictable contact resistance change here. So what we monitored in our book, obviously, because the contact surface is changing here after your probing. So it means you have to do something about this, and we suggested new technology using soft hard probing interface using liquid metals. Yeah, and this picture is self-explaining, I guess. So this is the reality. So you cannot predict the contact area during the high frequency measurement. But if you put a soft interface using liquid metal, and you can do this in ECM, yeah, I've shown you before, then you have always the stable contact surface here. And as a result, you don't have any change in contact resistance and other scattering parameters. Yeah. And you can see here how we implemented this. Yeah. So the results are pretty promising here. Yeah. Well, and there are two implementation ways, of course. You can use a liquid metal probe, how we call this. So you just pick up some liquid metal and use this droplet as a probe all the time, just probing the surface, like you can see here in this video. Yeah? Or you can do wetting of contact pads. You know, you put some liquid material here, and then you apply your high frequency probe, and you always have the stable contact area here. Very promising application. Yeah, probably we will have another spin-off company in my division very soon here related to this application. Automated nanobits handling. So maybe the last piece of work what I can present you in this time. Well, the problem behind of this research work, and this is one of the earlier projects here, is that I mentioned this already, all the labs use just the tip of the atomic force microscope because there are no options for other tools at the nanoscale. And with pretty good guys in Europe, we decided to change this situation and develop so-called nanobits. Nanobits are arbitrarily shaped tools which you can fabricate, for example, by FIB milling or even by surface micromachining. Why not, right? So you can do a charge of such differently shaped tools, and then the task implemented by nano-handling robotics is to pick up the tool which you need for your application and apply this tool on your tool carrier. Yeah? So I don't have time for this video. You are going to see, or well, maybe a couple of seconds. Yeah? I'm watching the time here. Yeah? So you can pick up one of such tools. So this is the fully automated procedure. This is the real-time picture from the scanning electron microscope. So the robot is carrying here a nanogripper, and this nanogripper is going now to pick up the nanobit and to carry this nanobit to the tool carrier, and then we apply anodic bonding here and then use this tool. Just one implementation. You can use the tool carrier here, and this is one of our nanobits, and this is so-called EFM super tip. So maybe some of you know super tip means, well, this is a specially tapered tip of the EFM cantilever with extremely high aspect of ratio, like you can see here. So you can go deep down into any structured surface at nanoscale. And here you can see the results of this EFM measurement here. After 100 scans on the same sample, you have pretty same picture. So this technology works just fine. Well, if you need more information, you can visit my division's website with plenty of information. I mentioned already the conference I established 5 years ago, International Conference on Manipulation, Automation, Robotics at Small Scales, short MARS. This is a flagship event. Unfortunately now, so we go through COVID-19 break, but we will get again 22 in Toronto, Canada, always in July. You are welcome to join the conference. You will learn the whole range of micro-robotic variations and applications at this conference. So appreciation to all these guys who worked or keep working for my team. Thank you very much for your attention.
Thank you, Sergey, for your nice presentation. So we have a couple of questions already in chat. I will start reading them. So first of them is, can you explain how FIP is used for imaging?
How TIP is used for imaging?
Yeah, certainly. Yeah.
You mean the tip of the EFM cantilever?
Probably I can pass the word for Ribi, who can ask the question.
Okay.
How FIB is used for imaging, focused ion beam. I think that was the question.
Okay, FIB. FIB. Okay. Well, this is very simple. You use gallium ions in your ion beam, and then you have a kind of secondary electrons emitted from the surface of your specimen. You know. So this is the same principle actually, like you use in the scanning electron microscopy using the electron beam. The only problem is that ion made of gallium are much heavier than electrons, and then the risk of damaging of your sample surface is pretty high. So you have to be very careful with controlling of the power of your electron beam. But if you know what you are doing, there is no problem at all, and you can get valuable additional information from ion beam imaging.
Thank you. Another question is the people observe that force units are not mentioned in some plot. What is the range of the force? What is the measured for example, van der Waals forces? Also, how is it measured?
How to measure van der Waals force?
Well, yes. And what is the magnitude of the forces that are measured?
This is piconewton area here, and how to measure the forces. I've shown this in one of our applications here. Just let me take a look. Yeah, this one. Yeah, this one. So this special project is about measurement of ultra small forces, actually. Yeah. So I mentioned the most recent project. So we got funding from German Research Foundation a couple of weeks ago. So this is exactly about this application. So you do force mapping here, for example, by measuring the angle between the surface of your liquid droplet and the surface of your specimen. So obviously, the higher the force, the bigger is the angle. Because otherwise, you can see this in this video. Yeah? So if you have smooth surface, the force is pretty high, and the angle is getting bigger and bigger because the surface tries to keep the liquid droplet here on the surface. So here you have a lot of spikes instead of a smooth surface. And for this reason, the droplet is going off pretty easily, and the angle is much smaller, you know. And this is a standard approach, actually, how to measure forces at nanoscale.
Thank you. I have one question, and just I want to have your comments for the audience. So a lot of people, they're familiar with the traditional industrial robotics. So you are talking about nanoscale industrial robotics. Can you highlight the key differences and the challenges that exist in the nanorobotics, micro robotics comparing to the traditional industrial robotics area?
Okay. Well, I mentioned this at the beginning of my presentation. We are talking only about industrial robotics, right? Industrial robotics, because micro robotics is a huge range of different types and applications. Yeah, I'm talking only about industrial robotics. Well, the major challenge is the speed of operation, and I mentioned the bottleneck for automation using robots at nanoscale is to get vision feedback in real time. The problem is that the scanning electron microscope is a brilliant device, but it wasn't intended to be a real-time sensor, right? So nobody thought in those times about application of this device as a real-time sensor. So the problem is very simple. It is a scanning technology. Any scanning technology is slow because you need time to pick up the information about the object point by point and line by line. And this takes time. So for this reason, many labs worldwide work now on how to increase the speed of imaging at nanoscale. So this is the bottleneck. But otherwise, well, industrial robotics at nanoscale is another science. You cannot compare. Why? Because, well, from the sensor point of view, I just explained, you use quite different sensor and you use quite different technologies to pick up the feedback information. From the actuation point of view, you use quite different materials and quite different drives. Why? Because at the nanoscale, you don't have gravity. And everything what you develop at regular scale for industrial robotics is related to gravity. Yeah? All your handling technologies, your tools, how you operate your robots, everything is related to gravity. Yeah? You fight gravity or you use gravity. At the nanoscale, there is no gravity. It means you have to develop everything from scratch. So this is a new science, actually. The major principle of automation, getting feedback and then adjustment of the position, is the same, of course. Yeah? So in the sense, we talk about the same implementation of automated robotic system, yeah? But the nature of the implementation is quite different. Yeah?
Okay, thank you again. So I would like to thank Sergej Fatikow for his nice presentation and to be a speaker of at our conference. So